But what we're going to talk about today is, in our opinion, applicable in different ways to places as far away as Greece, where there's also semi-arid, heterogeneous fuels in shrub or steppe types of vegetation. So again, there's about 20 different people in our team. We have specialists like Jake in fire simulation modeling, specialists who lead the Department of Interior, who, by the way, the US Geological Survey, who we are part of, is the science arm for the Department of Interior, which is one of the largest landowners in the world. And we lead the research and development on control options and ecology of exotic annual grasses, which I'll show you are fire promoting agents on these landscapes. And so one thing that's cool about the fires team is it's for the most part a one-stop shop for all things monitoring, detecting problems regarding invasions and fire, and coming up with solutions and implementing them over large landscapes. Okay, so this is a set of pictures which does a fairly good job of depicting the context for our work. So here on the upper left, you have a photo of the iconic sea of sagebrush that, at least in the past, characterized much of the western US. And in here, if you know about fire, you can see some heterogeneity, which is really important. You've got medium-sized woody species that can burn well, and there's wood in them. So when they burn reasonably hot. They're 1 and sometimes 10-hour fuels, separated by bare soils, and those bare soils have air in them, which obviously impedes the movement of a head fire and forces it into to flanking fire or sometimes extinction. And if you look really carefully in here, you can see patches of perennial grasses and little indications of soil biotic crusts. And historically, hundreds of years ago, small fires would occur in these landscapes, and the shrubs, which are mostly non-resprouting and must recover by seed, they would come back eventually. However, over time, an invasive annual grass known as cheatgrass invaded these bare soils, especially where the bunchgrasses were lost to grazing regimes which didn't match the ecology of these sites. And the cheatgrass forms it's straw-like and not green for most of the year and fine textured. It catches fire and passes fire readily. And so the other problem with cheatgrass is not only does it greatly increase the frequency of fires, cheatgrass is also very competitive after fire. So instead of having a cycle of going back between these states, you eventually convert to a fire-prone annual grassland. All too often, managers have accepted this level of decay, causing about half of the once 1 million square kilometers of sagebrush steppe to be at least partly invaded. And now people are focused on finding ways of directing the change towards tolerable states, such as by introducing fire-resilient and exotic grass-resistant perennial bunch grasses like Siberian wheatgrass or crested wheatgrass, also from Eurasia. So here you can see that the fire conditions are greatly moderated in this seeding compared to the surrounding invaded landscape. So the problem that we have is this is all occurring at huge scales. And we need to inventory the problem and then figure out how to manage it. And the management in this system is one of the most intensive and extensive restoration efforts globally. The tools involve using pre-emergent herbicides that are broadcast sprayed over huge areas at very low application rates. They inhibit the germination of anything, which any type of plant, which is a selective disadvantage to those exotic annual grasses like cheatgrass. And if the desired native perennials, especially the resprouting ones, are depleted, then we might get into some various forms of seeding, pretty expensive to do. And furthermore, we can address the causes of the problems by adjusting our land use practices, which oftentimes means at least temporary adjustments of livestock grazing, which is a passive form of restoration that's very expensive and needs to be planned very carefully in time and space. So the trick is getting information across these huge landscapes. The management units can range from pastures that are maybe 10,000 to 20,000 acres or hectares to areas that are upwards of a million. And they tend to be relatively uninventoried. There's not many roads. A lot of times the landscapes are rugged. It's hard to get in there. So the challenge is to get information, usually gridded digital information that is suitably accurate and reproducible so that we can have the information needed to make good land management decisions. So enter the problem of heterogeneity. Already you're probably imagining, okay, digital information, probably coming from satellites. It's probably at 30-meter pixels or coarser. Is it resolute enough to capture the meaningful changes in the ground? We already talked a little bit about that fine-scale heterogeneity that occurs within a plant community, like on the scale of a meter or less. That heterogeneity greatly affects fire behavior. But how about the larger patch scale changes that happen? Can you see that? You can see this clearly from the ground. Here's a photo that very clearly shows an area that's been invaded, probably was burned, and next to this nice intact landscape. Can you pick up these differences in the digital data that comes from remote sensing? And the answer is yes, you for sure can at some large scale. So if you're just looking over the entire Western US or the entirety of the semi-arid portions of Greece, probably it works pretty well. But most of the land management is occurring at much smaller scales. So at what scale do these techniques begin to have challenges, and how can we adjust for those challenges? Here's another cartoon of it. Here you can see an area that's been invaded by cheatgrass next to an area that is desirable native bunch grasses. Very different fire behavior, very different resistance and resilience in terms of the propensity of this landscape to be stable and staying the same. However, from Landsat or most other satellites, at first blush, these landscapes are relatively indistinct and hard to tell apart. Grass is over here, grass is over here. These two cover types will also be part of one of the most fundamental ways that we map vegetation for wildfire fuels management. So we can map the community types. At one scale, this might all be mapped as a grassland. At a finer scale, this might all be symbolized as annual grassland. This might be symbolized as perennial grassland. We also might map this in terms of fractional cover. This would probably map out as 80% grasses, cheatgrass, and this would map out as maybe 50% perennial grasses, so fractional cover. Or we might map this as, this could be mapped as what's known as a fire behavior fuel model. And this could be mapped as a low load semi-arid grassland. And the code for that for Scott and Bergen's database of FBFMs would be a GR1, grass 1. GR2 would be more fuels, usually for a wetter area with taller stature, denser grasses, and so on and so forth, up to levels 3, 4, and 5. So you could have grasses GR1, shrubs would be SH, And then the combo of grasses and shrubs is GS. So Scott and Bergen give us a library of 40 different FBFMs to pull from. Are those resolute enough? And how can we accurately map them on the ground? This is where tools like LANDFIRE are absolutely critical. LANDFIRE, based off of, most of you know about it already. It is parameterized in part from Landsat imagery. Another source of information that is now slightly more resolute, now down to 10 meters resolution, is the Rangeland assessment platform, readily available online. A sister or cousin to RAP is RCMAP. This is a USGS project. All of these form the foundation from which we start our scan and inventory of the vegetation and the fuels across the large landscape units that are the management units in the Western United States. So again, huge landscapes, big areas. We can't put boots on the ground everywhere. We've got to rely on these types of tools. LANDFIRE is pretty handy because it's just a deep set of many different data types, links pretty readily with some of the fire models. Is it accurate enough for, off the shelf? Can you just simply grab this and run with it to get accurate mapping of fuels and modeling of fire at the scale at which managers decide which treatment to apply, where and when, and what were the outcomes of that treatments? And the answer is it's imperfect, but the good news is that there are ways to improve it, and those ways are getting better and better literally by the week. It's a super exciting time to be in this line of work. And that's in spite of all of our challenges lately with science and support of land management in the federal government. So FBFMs, how to map them. This is kind of an outline for the talk today. We're going to talk about a set of different large landscape projects. One was the Soda Wildfire. Another deals with national park sites. This is 300,000 acres. This gets up to like 1 million acres. And then we're going to look across many different land ownerships in the Department of Interior, 4 million acres, and then come back around to super high resolution, moving into the Department of Defense, all these major landowners. So first, we're going to focus on the Soda Wildfire. This happened in 2015, right here, close to Boise. 300,000 acres burned along the Oregon-Idaho border. This became a focus area and focal project for all things dealing with fire in the Department of Interior. It has since become by far the very best well-studied wildfire anywhere on Earth. There's something like 50 publications now, mostly from our team on this. And so here you can see the range of elevations, lots of ecological variability, and the fine lines in here show all of the different pastures and management units, 105 of them. All the points show 2,000 plots, field plots, that were measured using standard rangeland measuring techniques every year, almost from 2015 to 2020, so the first 5 years after the fire. And then we just finished the 10-year monitoring. Pretty exciting. And initially, the mode of operation by the agency was to try to use remote sensing and a graduate student to monitor the outcomes of what was the most intensive set of herbicide and seeding treatments done to stave off the cheatgrass fire cycle. And here's a graph showing something that we've learned from the accuracy of RAP and RCMAP. Here's field estimates from these plots. Here's the remotely sensed model of cover based on satellite imagery. And a one-to-one agreement would be shown along the dotted lines. And here you can see for shrubs, in spite of their wide range in abundance, there's a tremendous offset. The model is tuned to much larger scales than 300,000 acres. Even though this is a large landscape, it's still small compared to this sort of model information. And because of that, we get what we call a false modern effect, where the vegetation estimate based on remote sensing tends to underestimate cover when it's most abundant, and conversely overestimate it when it is least abundant. And this is especially bad when you look at things like litter, which matter a lot for fire. Same thing with bare soil. So here we've shown that you've got to be careful and selective and strategic in how you use these kinds of tools. So one of the modes that we operate is with skeptical enthusiasm. So first, a test of assumption on how well these models work. And now with our enthusiasm, we're going to figure out how to still make use of these tools, because the bottom line is we still have to use these tools in spite of our recognition of their strengths and weaknesses. So Jake reconstructed via simulation the 5-day progression of the Soda Wildfire. So Jake, the ignition was somewhere right down in here?
Yep, so the star marks the ignition.
And then it passed to the north?
Basically passed straight north the first 2 days, and then that whole chunk turned into a big, huge flanking fire, which then was pushed to the east.
Great. And so up here, what have you mapped for us? You've got...
so what you're seeing, panels A and B, these are the... so you have the original 13 fire behavior fuel models, and then the Scott and Bergen 40 fuel models. And so these are outputs from LANDFIRE.
And from that, then he ran a maximum likelihood scheme that asked what map of FBFMs could accurately reproduce the wildfire. And when he did that, here you can see he got reasonably good agreement. Still some side and back burning, but the overall map of the fire progression looked pretty good, passed the eye test. And on top of that, some of the characteristics like flame length, rate of spread, heat intensity also looked reasonable according to the agency wildfire experts. So here's a map of what the FBFMs looked like based on what RAP was telling us for fractional cover. So you can find more about that in that paper. And the coolest thing to me about this was that another fire occurred nearby. This is about 30,000 acre fire, the Cherry Creek. And we were able to apply that routine without reproducing the routine, just apply the lookup table and then rerun Farsight, and we got excellent accuracy on this. It was we were able to simulate this burn within almost 90% accuracy. So that was pretty exciting. So moving forward now, let's look at it.
We should mention that the previous method did involve a lot of circularity.
Yes.
And we make note of that in the publication. And so
because we didn't have any field data, so we never directly observed the FBFMs. Now we had a chance. The National Park Service is very concerned about their extensive sagebrush steppe, like this 1 million acres in the Craters of the Moon area, and then the City of Rocks down here, 1 million acres combined almost. Annual grass and the wildfire associated with it are encroaching. They're very concerned. They asked us to come in and do some monitoring and mapping. Here you can see that the Jake and Chad and their crews sampled, about 1,800 plots in about 3 pay periods, so 3 biweekly periods. So people say that kind of monitoring is not feasible. They proved that it is. And the information from this was excellent. So we knew firsthand from the field what the fuel models were.
And to step back real quick, a lot of this work with the Park Service, right, was only possible through kind of a co-production project with the Bureau of Land Management, Fuels and Fire programs to kind of what's the word I'm looking for here? Build this photo guide.
We had a photo guide that so Jake published a very accurate, deep photo guide, which is cited in these papers. Recommended to you all if you haven't seen it, as an example of how to facilitate field monitoring of and field verification of FBFMs. Very important to do. So here again, you can see if we just look, if we take our field data and match it up against the RAP estimates, a lot of inaccuracy, but nonetheless, if we can use this information, the RAP estimates, and combine it with, let's see, a little bit of a typo here on the slide. We can combine it with the field data to use random forests and produce a hybridized, more accurate map from which we can then remap the fuels. So I'm trying to remember which color is our estimate.
So
is purple or yellow?
I would say purple is going to be LANDFIRE's estimate.
Okay.
So these.
Okay, so the purple is the number of plots across the landscape that LANDFIRE was telling us was present for each of these different field ed models. So some of these are grasses, some are shrubs, some are grass shrub, etc. And the yellow was our estimates. And so here you can see for some of these field ed models, there's very big differences. Sorry for that typo again. And here's some maps of how different some of these are. So LANDFIRE was confusing grass or shrub, for example, in many cases. And that had a huge impact on the fire risks modeling for this landscape, like the likelihood of burning, for example. So here for Craters of the Moon, you can see a burn probability map based only on the stock LANDFIRE images. When we instead use the field-informed, which is combining RAP and our field data to map out the FBFMs and then run the fire model, you can see something that's quite a bit different, and here is showing the difference. So LANDFIRE overestimating fire risks in a lot of places and greatly underestimating it in others. Same thing at City of the Rocks. These were fairly consequential risks. These managers were using LANDFIRE to plan their field treatments and estimate risks. Both of these parks harbor very high value 5-needle pines, and here, right in here, is the northernmost extent of pinyon pine in the United States, so really high value. We then use this, our fires prioritization scheme can use that sort of accurate modeling to predict, will it burn? And then the other question is, well, what happens if it burns? If there's a lot of perennial grasses that can resprout, and there's not a lot of woody plants that can't resprout to begin with, and there's not much risk of invasion, well, maybe the reburning isn't such a big deal. Conversely, if you're starting to have high abundances of exotic annual grasses, and you have low abundances of perennial bunch grasses, like shown here in the blue, then you've got a problem. You've got a high risk. If they're going to burn and they are poised to get readily invaded after the fire, these might be areas to prioritize your expensive and sometimes controversial herbicide treatments. So the parks took these data and indeed applied this scheme and applied treatments amazingly within it was about 6 to 7 months after we collected the field data. So really fast turnaround. It was really cool. We're doing the same sort of work for naval, Army, and Air Force and National Guard bases. There's about 4 million acres of sagebrush steppe in the western U.S. And obviously military training in these semi-arid environments. There's a risk of starting fires, and the disturbances sometimes can increase invasive grasses. So you've got a recipe here where incursion of the grass fire cycle is a real concern. Jake and Chad are leading and taking all of the types of approaches now and applying them to these landscapes. And here you can see fairly dramatic improvements over 1 million acres of, for example, the Fallon Naval Base here in central Nevada. So pretty excited. So moving forward, we've now expanded across all these different management units, and we're looking at like what happens after you do these herbicide or seeding treatments. How much have you actually reduced the fuels, and can you tell using the remotely sensed data over these vast landscapes? And what can you learn from using the field data? Like, how do these things differ? So here we've asked over many, many acres, actually a couple million acres, that in areas that received post-fire seedings to increase those fire-resilient perennials, or herbicides to reduce the fire-prone exotic grasses, or not. By the way, we use a very careful statistical regime to remove bias in where managers, so managers selectively apply their treatments. That introduces bias. Chad has pioneered the application of propensity score matching to help us strip out that spatial bias and all the confounding factors. And here, surprisingly, here what you can see is a fairly modest effect, treatment minus untreated differences in the probability that the GR1 or GR2 fuel bed, et cetera, shrub 1, shrub 2, unburnable, grass shrub over here, and shrub 1, shrub 2. Notice how many of these FBFMs really don't change that much as a result of the treatments. Some of them do, and Jake, those tended to be
grass-dominated fuel beds or the grass shrub.
Yeah, GS2. So when you map those out onto the landscapes, there's a little bit of an effect. So here you can see the treatments in hatched areas over these huge areas. This is I think this was the snowstorm fire in Nevada.
Oh, this is Bear Den and Craters of the Moon.
Okay, thank you. Bear Den fire. And this is the 50 percentile for very risky fire weather. And it's actually kind of hard to see that the treatments have affected the actual simulation of fire. So this is making us realize that not only do we have to be super careful in mapping these FBFMs, but we also have to ask the question as to whether or not the FBFMs are good enough. Are they resolute enough, both in space and how we map them, and in their categorical resolution? So that paper I just showed you is in review. Here's another one that's also in review. These should get released here anytime in the next couple of months. One's in landscape ecology, and the other one is in fire ecology, I think. Yeah. And so here, what you can see is we're trying to come up with decision trees with which one can take your fractional cover maps, for example, showing LSPG, large statured perennial grasses, combining them with shrubs and the amount of litter, etc. You can create these decision trees to help you figure out the myriad different ways that different cover combinations can land you or cause you to want to assign a site to being a certain fuel bed. So this is pretty exciting for us. We're using this now. That tells us, by the way, that there is a one-to-many relationship of an FBFM to different community types, and especially to different fractional blends of fractional cover. So moving forward, Chad is really pushing the envelope here recently by taking those random forest models that I talked about a little bit before, National Park Service, and using them iteratively and in deep learning, machine learning applications to end up with ultra high resolution FBFM maps. Super exciting, very iterative. And here's some examples of how that random forest approach is improving things quite a bit. So first of all, you're starting with RAP.
Correct. So we're talking about resolution, and in order to get better resolution, we need field-informed wall-to-wall maps of fractional vegetation cover. So we're pushing the scales of what we did in that MPS paper and providing more accurate fractional cover estimates using, first off, localized and temporally recent field data, in addition with phenological indices.
What's an example of this? And you're using Google Earth Engine for that. right?
Sure. Yeah. With Google Earth Engine now, they have a deep repository of both imagery and analytical power to derive important
field types, like cheatgrass. So like cheatgrass, I already told everybody that it tends to have a flashy growth pattern. So it greens up early in the spring, contrary to most of the other native plants, and then it senesces really quick. So that sends a very unique spectral signal in time and space. And then there's other plant types may not have as strong a phenological signal that the spectral, the database or the archive of different satellite spectral phenological indices in Google Earth Engine, they may not characterize those other plant types as well, but it's still pretty useful, right?
Yeah, totally useful, and we're getting, accuracy values higher than we ever have, especially for exotic annual grasses, because Matt mentioned I have a very distinct phenological signal.
So here's an example. So here's invasive annual grasses. This is estimated from.
So that's compared to the new RAP 10 meter, which is a vast improvement to their 30 meter resolution. But then further improving on that, field correcting that, we're getting, R squared values.
This is it right here?
Above 0.6, and this is going on right now, and we're getting values 0.7, 0.8 for some landscapes.
And Chad is doing this. This is all occurring on our supercomputing capacity. This is here. You've got this run over 2 million acres. These are plots broadly distributed over a massive area, burned and under area. So very pleased. So this is step one, random forest. Step one. Step two then takes the continuous cover of random forest and just like we told you before, selects out the appropriate FBFMs, but at a 30-meter scale, right? And you get something that looks like this. But then the cool thing is, and that's random forest 2. And then step 3 is entering deep machine learning with CNN, convolutional neural networks, so fancy word, in which Chad will start with this 30-meter point, but then combine it against NAPE, that stands for National Agricultural, I forget what I means, program imagery, or planet scope imagery, which is 0.5 meter, plenty resolute enough, okay? And you end up with a FBFM map that looks something like this. And what's cool about this is now you're picking up all that heterogeneity in fuels that will be much more likely to capture for example, the breakup of a head fire into flanking or backfires. So this is super exciting for us. And here you can see, for those of you that are into deep learning, you can see here the many, 50 iterations. You're doing iterative training and validation over and over again via supercomputing. So as the computers, our local computers and the supercomputing and the Google Earth Engine are improving, and we're getting more and more of this resolute imagery, well, the good news is we've got the tools to start making the maps that have the fine-scaled information we need over pretty big, not huge, but pretty big areas. So pretty exciting. So thank you. So let's just summarize. So we need the FBFM maps. Current LANDFIRE maps are awesome at really large scales. When you start getting down to the scales at which management occurs, caveat emptor, better be careful. You need to calibrate. Very pleased that Megan and her colleagues have emphasized that recently. Calibration, it's needed. What is calibration? Well, could be some of the things that we talked about today. So how are we doing that? So we improve those FBM maps beyond the foundational LANDFIRE via always using other people's models. There's a lot of work that the RAP program does to produce estimates of continuous cover from Landsat and Sentinel. We always use that. When we can get field data, we definitely use it. We try to avoid this circularity of using fire boundaries to back inform our selection of FBFMs. Why do we not like that? That's a poor modeling technique. It greatly limits transferability. Even though we showed it has some within region transferability, this model, if you try to move that model 1,000 miles away, it's probably not going to work. Whereas these other modeling approaches are much more likely. Random forests using carts, and especially the deep learning, have a lot of prospect. So there you have it. That's our approach. It's always improving. It's highly imperfect. We embrace that imperfection. We also embrace the heterogeneity and the variability in the landscape as opportunities to improve our ability to map, plan, and have good effectiveness of fuels management and wildfire risk management across our landscapes.
Hey, Inga had a question. Would the early annual grass product from RCMAP fit into this work somehow, so you don't have to calculate that yourself?
Absolutely. Now, keep in mind that map, we haven't worked too much with it. We've worked with Stephen Boyd's real-time cheatgrass mapping, and I'm assuming that what he did is now, I'm just guessing that that's been imported into RCMAP, into this new product. Some of what Chad is doing uses some of the same technique. Now, RCMAP is aiming to have accuracy at a very large scale. We need that. Like, we need to know what's going on at the, nearly the continental scale, right? The key difference with the fires team here is that what we're trying to do is drop down and to obtain the greater level of resolution needed for management scale. Could we and should we be using that new cheatgrass product in RCMAP? I think so. Yeah, I'm good. That's a great idea. But know that we would never use it off the shelf. We might test its accuracy first. We would expect that would do pretty well, but everything has imperfection. So we characterize that imperfection and then see, can we improve upon it with our method?
So just to follow up, Matt, I think Michelle Jeffries commented in the chat too, is Matt Riggy has kind of taken it upon himself to do kind of a major overhaul. And so, yeah, I think it would be good to check back in with Matt Riggy on that. And LANDFIRE has been talking with Matt about, the potential of using the kind of that frequent EAG product to adjust fuels and, adjust the fuel models in the area. So it would be good, I think, for all of us to sort of talk and figure out kind of, maybe what the best way to go about that, for sure.
Sure, we're available.
Cool.
Hey, Matt, I have a question.
Mm-hmm.
So great presentation. Awesome. And I just want to make sure with the 30 minutes there that I'm capturing this, and really what this, or at least the way I think, we're basing everything on imagery. We still got to go out in the field and do the field modeling also too, but this overall is just the imagery, correct?
Yes and no. Sometimes you won't be able to go out in the field. There's going to be scenarios where, here's a great Department of Defense where we're working now. There's areas of UXO, and you just can't get out in the field because the risk is intolerable, and they have very strict rules about accessing some of those areas. Another application is eventually everything that LANDFIRE is used to guide active suppression, right? So when the fire is burning, if we're trying to guide resource deployment for active fire suppression, there's no time to get field data, right? However, the first chapter of the presentation, in which we showed how Jake was able to greatly improve the fire risk modeling in hindsight, as a retrospective analysis for the Soda fire. What that actually, even though we had done a lot of monitoring. We were familiar with those landscapes. That analysis, I want to emphasize, was not actually parameterized by any field data. So what we're suggesting is that in some cases where you absolutely can't get field data, you can and should still use RAP and these RCMAP products that we're talking about as a surrogate. Okay.
I'm also thinking the decision trees produced from the Reburn project, right? That can be used to inform some sort of clustering or classification from OpenSense.
Yes. Yep. So all of those things can help you get a much more accurate FBFM map without you going into the field. That's the first answer to your question. The second answer is if you can get out in the field, and hopefully you can, you will greatly improve the parameterization of vegetation and your map of fuel models. And that's going to greatly improve the accuracy of your fire modeling. So always go to the field if you can. But if you can't, there are currently ways to use the remote sensing models of vegetation to improve upon what LANDFIRE can tell you about your managed landscape, your landscape unit.
Thank you.
Yeah. Thank you.
Matt, I'm not sure if you can see the chat window, but I'll just read a question from Christian. Have you ever noticed any situation where the satellite imagery doesn't match up with the reality on the ground? For example, let's say what looks like sagebrush on satellite is actually a different plant community when investigated in the field.
Absolutely, yes. So I actually showed some graphs like that. Can I go back and just scan them?
Yeah.
Okay, thanks.
Go back. It's the...
Chad, how did you get that? Oh, there we go. Oops.
I'll keep going back.
Okay, that's pretty good accuracy. But here's the nominal one. If you were just simply,
This one right here is the one.
Yeah, so here's one. So this one is over 1 million acres. This is about almost 2,000 plots. And here are many examples where in the field we saw, shrub cover. The model, our model based on field data only was telling us there's areas that have 50% shrub cover, whereas the remotely sensed model is telling us there's maybe 5%. And conversely, there's areas on the landscape, some, but not all plots, some plots. In the field, there was clearly nothing, but yet the satellite model in some cases told us there was 25%. So there's, over in here and over in here, yeah, there's some pretty major disagreement. Look at it for bare soil cover, even steeper. Steep also for these major targets, herbaceous annual cover like that. If you look at the spread on this, look at the scale here. These are pretty major disagreements. The means might line up pretty well, but when you start looking at the distribution of agreement, things really spread out. This doesn't mean that the vegetation models based on remote sensing are not useful. What it does mean is that if we want to use them, we have to be creative. And we have to very carefully frame our questions and our applications so that they are in line with the uncertainties associated with these models. Let me ask if that answers the question so far. You have something to say?
Well, and then just to add to that, Christian, so these photos here, so even though all three of these are not from the same plot, these two photos here are. And so so basically this is a single plot. LANDFIRE classified this as a grass shrub. So this is just an example of what that grass shrub looked like, but this is actually what that plot looked like. And so what you're seeing here are a few scattered shrubs, a field bed dominated by grass. And so we would have classified this as a grass. And so this is one common issue that we've kind of seen throughout a lot of our field observations is LANDFIRE tends to call a lot of things grass shrub, but in fact, what we find more often than not is something that is more or less shrub dominated or grass dominated. And so just another example of kind of a mismatch between field and remote.
Yep, it's hard.
And it is difficult. You can see from these three images that, yeah, trying to tell the difference from remote would be difficult.
Man, I have another question.
Yes.
LANDFIRE. What platforms out there does LANDFIRE exist in or has a part of an existence? As an example, WolfDis, and a little more on the wildland fire interpretation.
I mean, WolfDis is a big one. LANDFIRE is kind of a component of the newer fast fuels. They're using that to do some of their modeling, some of their landscape modeling.
Which involves fast fuels as an advance in terms of the 3D. So beginning to, this is super exciting. This is really the developmental edge of fuels and fire modeling. I just want to point out, all of the modeling that we showed you today is of the Rottermel sort. So it's two-dimensional. It's pretty good at picking up, point vertical heterogeneity at a point, but does a very poor job of modeling the interaction of fire at one set of XY coordinates compared to adjacent XY coordinates. I mean, 3D modeling obviously is based on pure physics and less on like the stylization of fuels that we do that is implicit with the FBFMs. So the 3D modeling is super exciting because it is what's needed to parameterize the physical-based modeling. So we're trying to work with fast fuels and Telemon. In fact, with luck, I think that's going to be our next phase of work with the DoD. That's where our research program is heading. And we will be creating formal crosswalks between these FBFMs and what we're calling 3D structural states. That's pretty exciting. But anyways, I digressed a little bit. Are we missing anything in terms of like what LANDFIRE is stitched into for platforms?
Stitched into all the Rothma products for sure. I think, Michelle, you've got LANDFIRE plugged into a few of your tools. The land treatment exploration tool will bring in LANDFIRE just for landscape management planning, not for fire risk analysis necessarily.
And Inga put in the chat window just to chime in. LANDFIRE is an IFTDIS, Wind Ninja, Blue Sky, the land treatment, like Michelle mentioned in the land treatment exploration tool. There's a link in there for that.
Yeah. Mark asks, who is Teleman? Oh, thank you. Yeah, so thank you, Inga. So Telemon is, you can Google it. It's a USGS. It's not mine. None of ours. It's a USGS hosted
repository.
Yeah, library or repository of
LiDAR point data sets, point cloud data sets.
Point clouds. Yep.
There you go.
Yep.
Andrew has a question, Matt.
Hey, yeah, thanks. That was a great presentation. I'm just thinking from the fire behavior modeling side, we're talking about some of these higher resolution fuel models.
Mm-hmm.
If we're building a landscape file, what about the other, inputs for that? And how do you guys go about making those high resolution?
Yeah, I mean, there are some high resolution DMs available, right? And so for some of those inputs like canopy cover, we've begun working on kind of a downsampled canopy cover product to go along with this fuels product. But yeah, right, downsampling some of those other topography type products. And then obviously, right, if you make the pixels smaller, the simulation is just much more computationally heavy. So we either decrease the size of the area that we are interested in, right, or we need to increase our high throughput computing potential. So does that kind of answer what you were looking for, Andrew?
Yeah, totally. I was just wondering if you guys basically resample LANDFIRE data for the other inputs, or have a proprietary.
Yeah, the elevation aspect, slope stuff.
Well, for the CNN, the deep learning methods, we're solely using imagery, and then it's learning based on the 30-meter pixel field corrected FBFM. So at the current state, we're only using for the super high resolution, less than a meter. It's solely based on imagery, and it's learning based off of our field corrected random forest.
Currently just predicting field models.
Yeah.
So yeah, we're working on it. But yeah, in the future, Andrew, right, having smaller pixels means more pixels, and so that's either a smaller area or a greater capacity for high throughput computing to get those simulations to run in a reasonable time.
Mark put in the chat. Mark is very open to chatting more about 3D data collection and analysis for fuel models and vegetation monitoring. So I'll make sure that that I get you that email address. He's from Utah State University.
Yeah, absolutely. Love to talk more about that.